You cannot escape proof assistance. Learner-centered design criteria for classroom proof assistance with Matthew Keenan.
Cool. Hello. Great to be here at my first splash. This is my first time, so I'm very much here to make new friends. So, like, if afterwards you want to chat to me, I'm very, very open to that. But yeah, I'm excited to be starting this discussion about how do we introduce proof assistants into the classroom, or how do we specifically like design them. So we're going to be thinking mostly about the kind of design aspect rather than the kind of technical programming language theory of like what actually is a proof assistant. So for a bit of context, I'm part of the Feature Programming Lab, so I work with Cyrus, who was the keynote speaker earlier this morning. We have this live functional programming environment in the lab called Hazel that we're working on, and we were thinking about, how might we add kind of proof elements to this so that we could, we've deployed this in the classroom, how might we be able to also in the classroom have some features where people can prove that their programs are correct. So my goal in the paper for HATRA was to collect all the experience reports I could find of other people that have introduced proof assistants into the classroom, and then try and pull this all together into a set of design criteria, which we can use to measure kind of how effective a proof assistant could be in a classroom, and to suggest experiment designs based off of that. I guess I won't have time in this talk to go over those experiment designs, but they are in the paper. But then, really trying to then use these design criteria to come up with designs for a possible future proof tools in Hazel. So there are actually like loads of experience reports. I guess I wasn't quite expecting this, but yeah, the work is quite spread out. But people have been introducing Coq into the classroom to teach math, Lean, Isabel, or creating all sorts of their own proof assistants. This table is also in the paper if you want to find all these citations. And if you have other citations that I don't have, then please let me know. I'd love to hear about other work that's going on in this space. But yeah, so the first sort of aspect of proof assistants that I want to talk about, especially for classroom use, is feedback. I think it's a real opportunity for proof assistants to shine. Proof assistants can provide feedback to a user writing a proof well before other normal ways of getting feedback. The usual feedback loop in proof classes is you write it down on paper, and the paper itself obviously can't complain about your proof. You have to wait however long it takes for the grading process to happen, or you have to wait until office hours. And while these are like high quality, valuable methods of feedback, I think if we can add supplement that with this iterative, fast process of getting feedback from a proof assistant, that has real advantages. And in particular, if you can get this fast feedback, it's easier to then put together like a mental model of what the proof assistant is thinking than proof classes graders. It's often quite hard to work out what the mental model of proof classes graders are. Like, how do you know if you've written enough to satisfy the grader? Or like, how do you know what they're specifically looking for? So I think this also gives us an opportunity to expose the mental model through that kind of feedback. So we propose two criteria for thinking about errors. The first is that they have to be clear and helpful. And the second is that you need to be able to know like how much of your proof is correct and see the things that are correct. And these are actually quite related to problems in compilers as well, right? We all know that compiler errors are not always that helpful, but there is research being done that we can probably borrow from in this space, particularly this compiler error is considered harmful paper. And likewise, in error recovery, we in our lab have got some work going on recovering from errors and making sure that errors only affect the bit of the program that actually has an error. The second sort of aspect I want to talk about is scaffolding. So scaffolding is a term from kind of learning theory. And I'll use it very specifically for, scaffolding is something that helps you construct knowledge, but at the end of building the knowledge, you have to take the scaffolding down. So it's different to a support in that a support, if you're using a support while learning, you can expect to use that support later on. Whereas a scaffolding, by the end of the class, you need to be able to not use the scaffolding as such. Yeah, these are our two criteria relating to scaffolding. So the criteria number 3 is that the tool has to help you, right? We think that a blank sheet of paper is kind of overwhelming to just start writing a proof on. Whereas if you have a proof tool, it might be able to give you some options, help you start writing a proof, and yeah, critically help you write a proof maybe when you otherwise wouldn't be able to. But there are problems with this, which some people have spotted when introducing these things to the classroom. For example, Guillaume and Narbo, when they introduced Educara, which is a point-and-click interface, 47% of their students reported completing several exercises by just clicking randomly. And likewise, Hans and Hobo, who introduced Lean, I think, people were randomly trying tactics. So that's why we added this other criteria, criteria 4, is that you have to actually learn something in order to continue. We don't want it to be possible to just randomly click and get through the task. But there's another issue here, which is that even if people have learnt how to write the proof in the proof assistant before they can proceed, that doesn't necessarily mean that that will automatically transfer to pen and paper. This is something that Nebelstoff et al. Discovered when they were using Coq. They were fairly convinced that the exercises were hard enough that you couldn't just randomly use tactics in Coq. But students, by the end of their class, were still consistently doing a lot better on Coq than in pen and paper. So when faced with this challenge of students' abilities don't naturally transfer from using a proof assistant to pen and paper, we've got kind of three options to deal with that. The first is we can just give up on pen and paper. I feel like that idea might actually be reasonably popular in this room, but I don't know. Most computer science courses still require quite a lot of proofs on pen and paper, and so we're going to try and tackle this seriously and think, oh, can we get students to be able to write pen and paper proofs by the end? Second option is to try and change our proof tools so that they're kind of closer to pen and paper to support the transfer. So you can think of using a proof tool that has, like, for example, if you're trying to teach people how to write deduction trees, you use an interface that looks like deduction trees. Or this example on the right is from Waterproof, which is they've taken Coq but replaced all the tactics with like natural language tactics. So it looks a lot more like a written proof, but it's still kind of Coq. So this is our criterion 5, and this is the approach that we're planning to take, is to use familiar notation in order to make that gap smaller. But it is interesting to note that the reason we want to make that gap smaller is not just so that people can learn how to use a proof assistant, but also so that they can stop using a proof assistant and do math without it as well. The third approach, which is kind of interesting approach, is to teach transfer separately. So these two, Boner and Kreitz, see mastering Coq proofs as like the first step in a long series of steps in order to get to the point where you can write a textbook proof. So maybe you learn first how to use a proof assistant, and then through a series of like adding comments until eventually the whole thing is just comments that look like a textbook proof. So there's another interesting approach that I think is worth looking into. But yeah, I think we're in our lab opting for the second approach there. We'll move on to some usability concerns. I think the first usability concern we often think about is the like verbosity of proof assistants, right? Like often, proof assistant proofs are quite a lot longer than pen and paper proofs. And some people see this as an advantage. Like it means that you have to write out all of the, you have to write out a lot more than you normally would, and so it makes logical principles really clear. And then, one particular example Kojin et al. Pointed out is that it makes the distinction between a proof and a proposition really clear sometimes as well, which can sometimes get obscured. But then on the flip side, this kind of extra verbosity does sometimes mean you have to talk about details that you would normally skip over. I like the phrase didactically inconvenient topics at awkward moments that Hans and Hobo used. But yes. Just, I guess, quickly going over our other usability criteria. For the classroom, it's good if people can pick it up quickly. It needs to be robust. If people are using a proof system that doesn't work, then they'll learn how to prove wrong, right? We want it to be easy to set up, which, so Emacs is not ideal. And we want, classroom integration so you can grade it and save the load on people trying to read through proofs. I also think it's important to remember that proof assistants are fun And no matter how we design it, I think we need to make sure that it keeps the kind of idea that it's, we enjoy this, and we want students to enjoy this, and students do say they enjoy it. One student said they felt it was like a puzzle, and this second student said that they worked on unassigned problems in Lean in order to procrastinate writing English essays. And I think we want that to continue, right? So to, I guess, conclude this talk, I will spend a few minutes talking about how we're taking these ideas forwards in our lab. So we've got two kind of projects creating kind of proof tools. So the first is the driver, which I think is currently in deployment. Cyrus is nodding. Great. Yes. So Jiao from our lab has been working on this driver, which I guess I can do a little demo. I want to lean over now. So the goal here is to teach students how to write kind of derivation trees for typing judgments. So we've got this built into Hazel now, so you can, we're trying to prove that this function application returns a number. So we'll find the application rule, typing application from the class. And because the objective here is for students to learn how to produce these proof trees, we don't want to do all the work for them. So this is again about doing the scaffolding rather than support. So the decision we took was we'll get the students to write out all of the hypotheses that they need. So now we're testing if I can remember what the hypotheses are. But in this example, we would need to show that the function goes from number to number. And then we'd also need to show that 2 is a number. Great. And you can see we get this kind of immediate feedback where the rule comes up as green if it's happy. And we've got all these feedbacks here saying, for example, if we're missing some things, it will tell us what we're missing. Or if we delete one of these premises, it will say we expected 2 premises, but got 1. Similarly, for the proof by induction, this is something that we haven't actually got a demo for, but if we're trying to teach students how to write a proof by induction, and we just give them an induction button that does all the work, then perhaps they won't necessarily learn how to format inductions, especially if this is the first time that they're learning what an induction is. So we're thinking, maybe you can click on the induction button, but you have to write out what the cases are or something. So in this example, you would have to say, we want a case for 0, and we want another case for y plus 1. But then there are, of course, other parts of this proof. Like, we're really not interested in checking students' ability to verify that x plus 2 is equal to x plus 1 plus x plus 1. Like, that is, I don't know, pretty basic algebra, and we don't. It's a mix of grade school stuff and didactically inconvenient axiom work. So why don't we just let them select it and replace it? So in this case, we're happy with that being a support because that's not part of the learning goals. So this I guess this to summarize this approach that we're kind of advocating is you got to think about what are your learning objectives, and the things you want to learn, you need to make sure that they're scaffolded, so there's something that you can take away even when you remove the tool from the user. And the things that you're trying to support, I guess, in order to make it as fun and not annoying as possible, you want to make sure that it happens fast and automatically. Cool. So I'm going to put, these are all the design criteria that we had in the end on the slides, and then open the floor for questions. Yes.
All right, I look forward to using a proof assistant that satisfies everything on screen. Who's going to do it? All right, questions?
So this is awesome work. I think I agree with basically everything you said. And I really resonate with the game, video game aspect of proof assistance clip, because there's definitely a lot of things I haven't learned because I've done agda proofs where I didn't even understand the statement of the theorem. I'm kind of curious if you have any ideas as to how this, like in that line, like if you have any ideas as to how that's, in particular, this like preventing people from like doing the like gamification thing scales to more advanced settings where you can't just like look at the derivation or have them construct a derivation directly. Because in part of my contention is like making people do things very manually is cool. But one of the really like magical things of learning things with a proof assistant is that it gives you a very good idea of like what is hard versus what is easy. And I guess I have like a cloud of questions around like basically like A, how do you scale this up, and B, how do you like place yourself like on this spectrum between like giving people a lot of things versus giving people like nothing at all? Because I think there's advantages to both like extremes.
Yeah. I think there's lots to be gained from the kind of like parallels between games and proof assistants, or games and kind of classroom tools. And I think there's some work. Game tutorials are like incredible ways of teaching people, and there's a lot we can learn from that. But yeah, there's a couple of big differences between like puzzle games and classroom things. One is puzzle games, like people drop off, right? Like not everyone makes it to the end of Portal, whereas like in a classroom, we would like everyone to make it to the end of the class. And then the other difference you mentioned, which was, because we have this kind of like transfer goal, or this goal that people can do things not just in the game, but like outside in the real world as well, then probably some of the kind of boringness does have to kind of creep into our tool as well. I agree. There's lots to think about there. And I think
I have a question. Can you, if you were thinking about, so say somebody wanted to take Lean or Coq or one of the modern proof assistants and make it more learner-centered using these criteria, which of these is the most important for proof assistants as they exist today, where it's like, if you wanted to prioritize your effort, you would say, start here. This is where we should be focusing our energy.
Oh, good question. I think the transfer issue, personally, is the biggest issue. Like, I guess going into this work, I was expecting it to be the usability. Like, I was expecting the biggest issue to be that Coq is difficult to use. And I think reading experience reports, it might just be that the experience reports are written by people that really like using proof assistants or whatever, but or by successes in classroom deployments. But it seems like the bigger issue is, people can learn how to use Coq, and then they just love it and then get stuck on Coq and move onwards. So I think the ones that relate to transfer are probably the most important. And I would say probably the familiar notation, because it's a really broad, I guess, criteria there. Like, there's the aspect of what do the symbols look like, but then also what do the proofs look like, and then you've got all sorts of different domains where the notation might look different. So I think there's a lot of work to be done, and I think familiar notation is probably the most important.
Cool.
So I think if you're talking about the kind of how much are we allowed to give them, especially in a classroom setting, I found most of our students, at least, just have trouble like starting the proof. So whenever we're designing like tools to help them, for example, we do a lot of proof of partial correctness in like automata theory. Most of them just want something for like to build a strong base case, and then from there on, if like their invariants are proven to hold, then they can easily like writing the proof itself, even if it's pen and paper, gets a lot easier. So I feel like if you kind of say, where can you go completely alone from here, like without any additional assistance, I feel like it's a good like line to kind of cut off any unnecessary help, if that makes sense.
Oh yeah. As in, you can tell whether you're helping someone too much by if they don't need the help. Then
it's more of like I feel like most people are just terrified of proofs because it's like they're throwing you into the deep end of like, where am I starting? So if you have like enough things provided to just build that base case, and from there on, most people are, at least I've seen that most people are fine. But that's maybe just our experience. We've had a lot of students repeat the same mistakes. So
yeah, I think I would maybe add like maybe it's the start and the end are the most difficult parts. Maybe like the start because you've got this blank sheet of paper. It's like, what do I do? And then the end, 'cause it's like, have I done enough?
Where do I say therefore, comma?
right. Yeah. But I can kind of see. Yeah, maybe the middle part is.
One in the back.
So I think like one of my memories of using Coq is that like it's actually just like a pretty satisfying UX. Like I like hitting the buttons and like seeing like things show up. And so I'm wondering whether like how much you've kind of explored proof assistance from that angle of just like the pure UX experience.
In terms of like
designing something that like people want to use.
Yeah. I guess I haven't delved too far into like the question of like, oh, if you change this, then does someone no longer want to use it or something? My general impression is that so far, in terms of the design space of proof assistants that have been deployed, they're all still somewhat fun. But yeah, I can see there probably are, changes you could make that would make the whole thing much more, I don't know. Like if you got people to type out proof terms for everything, then maybe that might take a lot longer. Or if you, delay the feedback. But I think that's an interesting question, is to think about what exactly makes it fun and which things can we play with without changing that. Yeah.
Really nice talk. I love this set of criteria. Now I want to evaluate my proof assistant sassy alpha according to them. But so I wanted to comment, maybe respond or validate your last statement about familiar notation and transfer. So we do sassy alpha is actually could be in your category of notations that try to imitate pen and paper, right? And we've always experienced very good transfer. I'm grading midterms in the next couple of days, so I can tell you if that happens this year too.
Nice.
But I actually think that familiar notation makes a huge difference, right? Or specifically pen and paper familiar notation, because then they're literally using a very close notation when they write it out, right? So anyway, it's a hypothesis, I guess. I don't have any counterexamples. I only have a positive example, but it also helps with the learning curve aspect, which you also have up here.
Yeah, thanks for that. Yeah, it's cool how it has like the two advantages. There's the transfer one way and the transfer the other way. It's both help by having the familiar notation. Yeah.
All right. Let's do one more question and get the next speaker going to come up.
Yeah, I think the question of transfer is really interesting because reflecting on my own experience learning proof assistance, like the first time I encountered a proof assistant, I was very much in the like, do random stuff and then it passes, hooray. And then I set proof assistants down for like a year or two, and then I took another class. I needed a proof assistant, and for me, it was really the transfer going from learning how to do the proofs on paper to then translating it to the proof assistant rather than the other way around that really helped me understand what was going on. And so I'd be curious if you, like one direction you might explore is like, well, pen and paper affords like less formal versions of a proof, and maybe it's part of it is like being able to do informal scaffolding on pen and paper is maybe one of the things that helps affords transfer ultimately, right? Like oftentimes our ideas start in this like we don't really know what's going on, and starting in a proof assistant is starting at the extreme formal end of that scale. So I wonder if there are ways to like, in addition to making the notation look more like pen and paper, like maybe take advantage of some of the other gradual aspects of Hazel to like bring in more of this like informal reasoning to a proof assistant context.
Yeah, hopefully, yeah. I think on, like, even if you're just thinking about pen and paper proofs, like, the mathematician's brain is always working at two levels, I think. Like, you've always got the kind of totally formal level, and then you've got the kind of, like, intuition. And like, whenever you're building a proof, you always got to come up with this kind of, like, intuition for how you're going to prove it, and then you're slowly making your formal thing match that, right? And I guess, like you're saying, in a proof system, we've got the most extreme version of the formal thing. But there's probably a really interesting question of, can you get the kind of abstract intuition on the page as well. Like I've seen some examples, especially for like geometry proofs, where you have half the screen would be, I think Educara does this in their kind of half the screen. They've got point and click, very formal proof, and on the other half of the screen, every kind of object you click on will show up as like a picture on the diagram of the of what the geometric object looks like. So I think there's probably lots of interesting stuff in that space of keeping those two levels on the screen as well in education. Yeah.
Cool.
Great talk.